Hi, with this video I want to talk about Gaussian processes. So this is a special class of stochastic processes, and we now have the mathematical tools to define what this process is. We can make a couple brief remarks about why it's a useful process for some of our analysis. Okay, so let's define a Gaussian process first. So we'll make a couple definitions. So let's define a vector of random variables. So I'll write x underline for a vector, and this is going to be equal to a vector of x at time t1, x at time t2, down to x at time tj, just to pick an index. Okay. So that's the process at j points in time. And let's define a vector u of just values of interest. Okay. So this will be u1, u2, down to uj. And so we'll say a random process, we'll say it's a Gaussian process if for any size j, where j is that index up above, the joint probability density function for the process at those j points in time. So I'll just write underline x and underline u so I don't have to spell all that stuff out. If that joint PDF is 1 divided by 2 pi to the power j over 2 times the determinant of a covariance matrix that we'll define in just a second. Times e, and hopefully you're seeing the familiar multivariate normal PDF of forming here, because that's what we're writing. So it's minus 1/2 u minus m, where m is a mean vector we'll define in just a moment, transpose sigma xx inverse u minus m. Okay, so there's a multivariate normal PDF, and then we just have to define a couple terms there, where the mean vector is the mean value of x at time t1, mean value of x at time t2, down to the mean value of x at time tj. So it's just take that mean function for our stochastic process and evaluate it at all the points in time t1 through tj that we're interested in. And then we have to define a covariance matrix. So the covariance matrix for x okay, so we need the covariance, well, we need the variance for x, but we can write this as the covariance for x at time t1 using our covariance function. That gives us the terms we need. Then we'll do the covariance function for x at time t1, let's go t2, t1. Doesn't matter which order we put those t1 and t2 in because of the symmetry we just talked about, but we'll do this just for organization's sake. Down to kxx at time tj t1. And then we'll go down the diagonal down to kxx. Make this a little bigger so I can just write a little more cleanly. tj. And then across, we'll go over to kxx t1 tj. And down. So we'll kind of fill in where the ith row and the jth column gets ti, tj as the indices on the covariance function. Okay? So we just evaluate that covariance function at a bunch of pairs of points in time. Okay, so So what's this saying, kind of big picture? So we're saying that if we take x, the stochastic process, and we look at j points in time, that the joint distribution of the process at those j points in time is multivariate normal, because it's got this multivariate normal PDF. And further, we can specify that multivariate normal PDF if we have the mean function for x, and we're going to evaluate that at the j different points in time. And if we have the covariance function for x, and we're going to evaluate that at all the j squared combinations of time indices that we're interested in. Okay? So that specifies our mean vector and our covariance matrix, and then that in turn allows us to evaluate this multivariate normal PDF. So if a process has this multivariate normal PDF defined as follows, we say it's a Gaussian process. Okay? So here's a few more words like that. Right? So the joint distribution of the process at any combination of points in time, right? So any set of j indices in any size j, were characterized by this multivariate normal distribution. And then we can note that we're completely defined by just that mean vector and the covariance function. And that's completely defined by the mean vector is completely defined by the mean function. And the covariance matrix is completely defined by the covariance function that we've been developing. All right? So that's what a Gaussian process is. And you can see kind of convenient to specify it because we just need these two functions that we've been working with. Further, remember back from the properties of multivariate normal distributions that linear combinations of multivariate normal distributions were still Gaussian. So we can say that linear transformations of Gaussian processes are Gaussian processes for the same reason. Okay? And so that's going to be pretty handy for us because if we have a Gaussian process load on a linear structure, we're going to do the response of that structure will be a linear transformation of the load. And so the response of the structure is going to be a Gaussian process as well. And so we'll stay in this nice Gaussian process world. All right. Here's kind of a intuition to think about what that means if we've got a Gaussian process. So here's my cartoon of the realizations of a stochastic process. And if we think about 2 points in time, say 10 and 20 off of these plots, we say, well, what's the joint distribution of this process if it's Gaussian? What's the joint distribution look like for these 2 points in time? So I could make a plot of x at time 10 versus x at time 20. And then I could plot contours of the probability density function. So let's say, well, x at time 10, it's going to have a mean value of whatever the mean of the process is at time 10. And then x at time 20 will have a mean value of the process at time 20. And then we'll have contours of a joint probability density function. So these are normal distribution contours. That's right, normal distribution PDF contours. So if I could draw well, those would be ellipses of kind of constant probability density. And so the means are defined by the mean function, and then there's going to be some variance of x at time 10 and variance of x at time 20 that'll come out of the covariance function. And then the autocovariance will also specify how dependent we are at time 10 and time 20 as a pair. And so if I picked those two times, I would have a bivariate normal PDF for this distribution. Right? And if I took 3 points in time, I would have a trivariate normal distribution. That's a little harder to draw. But that's what's going on. Okay? So that gives us this kind of nice mathematical way to talk about the likelihood of occurrence of any combinations of x values at any combinations of points in time. If we have a Gaussian process, we can just get that all out of the multivariate normal distribution. And then nicely, that distribution is completely defined by the mean function and the autocovariance function. Okay, so that is a Gaussian process definition. And that's all for this video.